So I'm going to record this session. And now what we're going to be getting into today are monomials. And what monomials are, they're a one-term expression or a constant or the product of a constant and one or more variables. Now these variables may have whole number exponents. Give me a second there to write that down. But the idea of a monomial is it's this one single term. That's really sort of the overarching idea. And we've talked about like terms in the past and combining like terms. And here we're just dealing with a single term. And we're going to look at multiples shortly. What we do with multiple terms. But with this one, it's just a single term. So examples of monomials, -3. So that's just a constant. Constant term, that's a monomial. That's a single term. Other ones that we've seen, 15, something like 15x, we've dealt with something like this. This is also a monomial. You have a constant times a variable. And we could get kind of fancy with this. We could have multiple variables. Constant times multiple variables. Or we could take a constant times multiple variables. We can give those variables exponents. And there's no limit to what the constants in front can be. The exponents, we're limiting those to be whole numbers, but the variable in front, we can let that be a fraction. That could be, this could be, say, a decimal number. We're not going to limit that. It could be positive, it could be negative. But all of these are examples. Each one is a monomial. So questions about that? Now, I will add this. The number in front of a monomial is called a coefficient. So the number that goes in front is a coefficient. Well, so for example, if we take 3x squared, the coefficient, I'm going to abbreviate coefficient, is going to be 3. For this one, 2/3 a squared b c4, coefficient, that's 2/3. And again, we see something like this. Even though there's no number written in front, there's going to be that invisible 1. So in this case, the coefficient is going to be equal to 1. And then likewise, if we have a negative sign, it's going to be negative 1. So any questions about that? So the next thing we're going to look at is multiplying monomials. And this is where we're really going to be using that product rule for exponents. And if I'm erasing too fast, let me know. Please let me know. So for multiplication, well, what we're going to do is we're going to multiply coefficients. You're going to multiply together those front numbers. And then we're going to combine variables. And this is where we're going to use that product rule from exponents. A to the R times A to the S will be A to the R plus S. We're going to use that rule to make these into a single, these two terms into a single term. So let's do an example. I'm going to pull some homework problems here. So let's say we have something like this. Three x to the fourth times 4x cubed. Now what we're going to do, we're going to multiply our coefficients first. So you have 3 times 4. And then we're going to have our variables, x to the fourth times x cubed. Now, because this is multiplication, the order and the grouping won't matter. So what this becomes is 12 times x, and then we're going to use this product rule on those two. 4 plus 3. This is going to give us 12 x to the 7. Questions about that? Now, let's say we got something complicated like this. Well, again, what we're going to do, we're going to multiply all the coefficients together. So we're going to multiply 5, negative 10, and negative 2. And then we're going to multiply our x's together. Our y's. And so when we do this, 5 times 10 times 2, well, 5 times negative 10 is negative 50, but negative 50 times negative 2 is positive 100. Now for our x's, we're going to add up our exponents. So we have a 6, there's an invisible 1. When you have a variable by itself, there's an invisible 1 for the exponent. And then we've got a 2. So this will be 6 plus 1 plus 2 times y to the 4 plus 6. So we get 100 x to the 9 y to the 10. So questions about that? So that's multiplying monomials. Next, what we're going to look at is dividing. In dividing, we're going to basically follow the same procedure. We're going to deal with coefficients, and then we're going to combine variables. So again, we'll divide or really reduce. You can also possibly look at this as like reducing fractions. So we're going to divide or reduce coefficients. Again, I'll abbreviate coefficients. And then we're going to combine variables. But now we're going to use the quotient rule. So we're going to use this. So you have a to the r over a to the s. And this will be a to the r minus s. All right, so any questions before we get started? All right. So for example, you have 15x cubed over 5x squared. So you can think of this, you can organize this in different ways. You can organize it, I'm going to do it this way first. So we're going to divide the coefficients, and then we're going to have, we're going to use our product or our quotient rule on our variables. So this is going to give us 3x to the 1 or 3x. I'm going to show you different ways of organizing this. And I think this is the book does this too, and I think it's just an easier way to see things. It sticks closer to the rules that we've studied so far. So I'm going to do this example again, but I'll show you a different way of looking at it. So here's the alternative approach. And this is really the best way, I think, to go about this. We can think of this in terms of multiplication to some degree. And we can treat this specifically like it was fraction multiplication. Like we had the fraction of coefficients times a fraction of variables. And so now what we can do, we can say, do our division or reduce this like it's a fraction. And so we get 15 divided by 5 is 3 times, and then now we use that quotient rule where we subtract the exponents. So we get 3 times x with an exponent of 1, or x to the first power. And that's the same as 3 times x, which gives us 3x. Questions about that? So let's do another one of these. Get some practice dividing monomials. And a lot of these things, I've said it before, I'll say it again. It's all practice. Building that intuition. So again, let's break it up into fractions. I'm gonna kind of skip a step there where we just go directly into a coefficients fraction and a variables fraction. Now 18 divided by 3, or 18 thirds, you can say that reduces the 6. This is y, and with the quotient rule, it's always your top exponent subtracting the bottom, regardless of what these numbers happen to be. It's always the top exponent minus the bottom. So you get something like this. Now, when we work with exponents, we don't want negative exponents. So what we do is we use that flip rule to make the negative exponent become positive. We can rewrite this without a negative as long as we flip it. And then if we multiply across, and again, you can imagine there's that invisible 1 that's underneath the 6 here. Multiplying across, 6 times 1 is 6. And 1 times y cubed is y cubed. Questions about that? All right, let's do another one. Let's pick out a real kind of complicated one. Let's see. So we're going to break this one up. Now, if we look at the top, we have an x, z, y, and at the bottom we have x, y, z. Now we have the same variables in the top as we see in the bottom and vice versa. But we could change the order on this. We can make it into a XYZ on top also. And again, the reason is that multiplication order doesn't matter. So we can rewrite this like so. And now we can break things up. Now, if you want to skip a step, I mean, you could certainly say, well, these are going to be coefficients. This is an X. These will form a Z, and then these will form a Y. You can do that too as well. So now we're going to reduce and combine. So negative 16 over 24. Well, both of these numbers are divisible by 8. So 8 goes in the negative 16 negative 2 times. 8 goes in the 24 3 times. And then that's not going to reduce any further. Now this will be x to the 3 minus 1. Again, a standalone variable always has an exponent of 1. And here we go again. Now we have a 1. Again, always the top minus the bottom. Always. 1 minus 7. And then 2 minus 1. And so what this will give us is negative 2 over 3 x squared, y negative 6, and then z1. But when you just have a 1 there, remove that 1 and just leave it as a standalone, well, not a standalone, but just a invisible 1 if you want. And that's going to be your answer. Any questions about that? Now you can make these a little more complicated. You can still do something, say, like this. Let's say we have this. So let's say you have something like this. Well, what we want to do here, let's multiply on top and multiply on bottom first. And we're going to do the division for last. This is very similar to what we did with PEMDAS, where we have these complex expressions, and we always save this large division bar for last. So let's combine the top. So you have 4 times 9 for coefficients, and then we have an a cubed, or a to the 3, an a to the 4, then a b squared, or b to the 2, a b to the 10, over 3 times 2 times a to the 5th times a to the 6th times b times b. So 4 times 9, that's 36. And then we have times a, and we add up the exponents, that's 3 plus 4, times b, that's 2 plus 10. And then 3 times 2 is 6, times a, 5 plus 6, times b. And these each have an exponent of 1, so this will be the 1 plus 1. So this becomes 36, a7, b to the 12, over 6, a to the 11th, b to the 2nd. So any questions so far? So this will be 36 over 6 times a7, a11 times b12 over b2. And then 36 over 6, well, that's going to be 6. For a here, again, top minus bottom. And then top minus bottom. So we have 6, a to the negative 4, b to the 10. Now we also, again, we want to get rid of the negative exponent, but we can only do that if we do the flip rule. So this will be 1 over a to the positive 4th. Can't just make it positive. We got to do the flip first. And again, we can treat these like fraction multiplication. So we have 6 times 1 times b10. So 6 b to the 10th over 1 a to the 4th 1. We have a to the 4th. And that's going to be our answer. So any questions about that? All right. So next we're going to look at addition and subtraction. So the idea here, and it's something that we see, but the idea of sort of gathering like terms. And so the idea of like terms is they have the same variable part. Now, the reason some terms would have the same variable part is, well, they would have the same variables. But also, these variables have the same corresponding exponents. So it's not just the same variables, but the variables need to have the same corresponding exponents. And again, I'll do an example here of what that's going to look like. But if the x has an exponent of 3 in one term, then the x also better have an exponent of 3 in the other term. Let's say we have x squared y. So we could say we have a choice of xy, xy squared, or 7x squared y. And amongst these, the like term is going to be this one. Now, this one has the same variables, but there's no square on the x, so it's not going to work. Now, this one has the same variables, and there is a square, but it's on the wrong variable. It needs to be on the x, it can't be on the y. Even though this one has a different coefficient, now in these, there's that invisible 1 for the coefficient. The coefficient doesn't matter. It's just the variable types and the exponents that matter. And so that's why this one is the like term. So just to emphasize, the coefficient, that front number doesn't matter. So for example, let's say we have something like this. And the way we do this is we typically, once we identify terms of the same type, we're going to end up combining the coefficients. So we have 3x squareds, we have 6x squareds. So that means we have a total of 9, or 3 plus 6 x squareds. And for the type y squareds, we have 2 of those and 5 more. So we have 2 plus 5y squared. So you have 9x squared plus 7y squared. And so that's going to be our answer. So let's say we have something like this. Now, again, what we're going to do, we're going to combine coefficients. Now, each of these is a type a cubed b, typed a cubed b, typed a cubed b. So this will be -2 plus 1 minus 12 a cubed b. And so -2 plus 1 is -1. And then we'll have a -1 minus 12. We'll get a -13 a cubed b. Questions about that? Now, sometimes what we can do is we can combine this with some distribution. And this is kind of an interesting thing to do. So let's say we do this. Now, the way we get rid of parentheses when we simplify is we distribute. So we want to get rid of these parentheses. So we're going to distribute this xy. So that'll give us xy times 1 plus xy times 1 over y. And again, we can treat this as if there's that invisible 1 underneath, so we can do fraction multiplication. So now let's combine things. Let's simplify xy times 1. Well, that doesn't change anything. Multiplying by 1 never changes anything. Multiplying across on top, we have xy. And 1 times y is y. And then what we can say is we could say this y and this y, they're going to cancel, just like we reduce fractions. We'll reduce the y's here in our fraction, or cancel the y's. And so we're left with that as our answer. Questions about that? All right. Now you could get something like this. I just want to point out one thing with that last example. If we take a look at our answer, this is a type XY. This is a type X. So these won't combine because they're not like term. That's as far as we can go with it. All right. Now for something like this, we've got monomial division, addition, and monomial division. Just like with PEMDAS, we're going to do the division first. So 18 over 3 is 6 times x to the 4 minus 1. I'm going to skip some steps here. Well, here, I won't skip the steps. I'll keep them all in here. When you get faster at this, it's okay to skip some of the steps, but you want to be careful. You don't want to accidentally, don't skip too many, don't skip too soon. Only when you feel you're ready. So this will be 6 times x 4 minus 1, and 3 times x 7 minus 4. This will be 6 times x to the 3 plus 3 times x to the 3 yeah, 6x3 plus 3x3. And so now we combine like terms. We have 6 x cubes. We have 3 more of them. So that's going to get us 6 plus 3 x cubes, or 9 x cubes. So any questions about that? So the last topic in this section, and it's turning out to be a fairly packed section. There's quite a few things in here. But we're working with scientific notation. What we're going to do is we treat powers of 10 like a variable. So, for example, if we're multiplying two numbers in scientific notation, let's say we have something like this. Well, what we did before is we'd multiply coefficients, then multiply variables. So same thing here. We're going to gather our coefficient, so to speak, and then we have our variable part, or in this case, our powers of 10. So this would usually play the role of coefficients. This would usually play the role of the variables. But instead, we're going to break it up into not powers of 10 and powers of 10. So we'll get 6 times 10. And just like with the variables, we use our product rule here, 3 plus 5. And so we're going to get 6 times 10 to the 8. That's going to be our answer. Questions about that? So we got to be careful with this. So for example, let's say we have this. So what we're going to do, we'll have our non-powers of 10. And then we have our powers of 10. So we'll multiply our non-powers of 10 here. And so we're going to get 22.72 or 22 and 7200ths. And then we're going to add the powers of 10, treating these like this is an x to the 16 and x to the 9. And so we're going to get what looks like the answer. Then we put that x there at the end. So, I mean, that looks like it's correct. But here's the thing. This needs to be between 1 and 10. It isn't between 1 and 10. So here's a trick you can do. We can put 22.72 into scientific notation. And so since this is a big number, we're going to move the decimal one spot to the left until it's a small enough number. And then the number of times we had them move left, that's the exponent on our 10. So when we take big numbers, we put them in the scientific notation, we move the decimal to the left until we get a number between 1 and 10, and then the number of spaces we moved that's the exponent on that 10. And so now we're going to take our answer, (22.72) times 10 to the 25th, we're going to replace 22.72 with 2.72 times 10 to the 1, and we still have times 10 to the 25. And now we just combine those 10s, we get 2.72 times 10 to the 26. So now we have the true answer. Questions about that? All right. So the last thing to mention was scientific notation. We could have division. Now, again, what we're going to do, we're going to break it up into fractions based on whether it's a power of 10 or if it's not. And before, again, this would be the coefficient fraction, and this would be the variable fraction. Excuse me. So we're going to break it up like that. Again, we're treating the powers of 10 like they're variables. So this is like x to the 5th, x to the 2. So we do our division. 8.4 divided by 2 is 4.2 times, and then we have 10 to the 5 minus 2. Or 4.2 times 10 to the power or the exponent of 3. Questions about that? Now, again, we can get into some trouble with this. Let's say we have something like this. Well, again, we're going to break it up. And again, this is like the coefficient fraction, and that's the variable fraction. So if we take negative 4.0, divide by 8.0, we get negative 0.5. And then for this, we'll have 10, and then top minus the bottom. Of course, we're going to get a double negative here. And we're going to get this. And it looks like we have our answer. But we've got another problem. The 0.5, now the negative part is okay. We're not going to worry about the negative being on here, but the 0.5 is not between 1 and 10. We've got that problem again. The negative we're not going to worry about. When we're talking about scientific notation, we're not going to worry about the negative. But the number here, regardless of its sign, it needs to be between 1 and 10. And that one isn't. So we got to fix it. And we're going to fix it the same way. So 0.5, we're going to write in scientific notation. Now, this is a small number. Excuse me. It's less than 1. So when we take small numbers and put them in the scientific notation, we move the decimal to the right. And then with small numbers, we're always dealing with negative exponents. So we'll have a -1, and that's for that one space to the right. But small numbers always deal with negative exponents. So now we're going to take our answer, -0.5 times 10 to the -3. We're going to replace the 0.5 with our number in scientific notation. We still have our times 10 to the -3. And these are all going to meld together. We'll get -5.0 times 10 to the -1 times 10 to the -3. And then we'll add these together. And so what we'll get, -5.0 times 10 to the -4. So any questions about that? Now, for the sake of time, I'm going to go a little further today. We're going to go over time a little bit. I'm not going to be doing a lab. We'll do a lab session, but I'm not going to have any lab work for today, just so you can work on your exam if you haven't worked on it. But I'm going to go a little further. We'll get close to 10 o'clock this morning. But I want to talk about a polynomial. And what a polynomial is, it's a finite sum of monomials. So if we take these monomials, these terms, and we add them together, we would get add or subtract. And the sum could be, you could be adding negative versions of these, or in other words, you could be subtracting. But here's a monomial plus a monomial plus a monomial. And that's a 3-term polynomial. And you could see something like this. This is a 5-term polynomial. So questions about that? So actually, I'm going to call it today because I'm just realizing we covered a lot of stuff, and we still have time to dedicate to these other sections. So given how far we've gone today, I'm going to call it. I'm going to say that's good enough. So we're actually going to finish just a little bit early. We'll get the polynomials next week. But if any questions about this, let me know. Again, we're not going to have any lab assignments today. I'm going to have the lab session open at 10 o'clock, just in case you have any questions about your exams. And other than that, have a wonderful day.